In this video we're going to take a look at Stoke's theorem. So Stoke's theorem relates the integral around a closed path to the surface integral of a surface capping that path. Now, a bit of a mouthful again, but it's really quite simple. So if we think about a capping surface, if we have some closed loop, say C1, I've also drawn a second one there, C2, then if we imagine we had a membrane over the top here, so that's in blue, then this membrane here would represent a capping surface. So we could think about that there, if you like, as a swimming cap. So the circle around here is the circle of your forehead, and the cap is the rest of your head with a cap on it. So what we're going to do now is we're going to take this surface, and I've drawn one out again down here, and we're going to split the surface into little polyhedra, and these polyhedra are going to sit normal to the surface. So they're just going to, they're going to sit tangential to the surface, so they're just going to cut the surface at one point. And you could imagine taking these little polyhedra, and we could take a limiting process where we increase the number of polyhedra to infinity and we decrease their areas to 0. So eventually, when we do that, then all these little polyhedra will eventually become a continuous surface, as opposed to being a linear jagged surface. So then what we're going to do is, after we've split that into the little polyhedra, we're going to look at the circulation around each of these polyhedra, and we're going to use the right hand rule as well. So the normal will be coming out towards us here in this little area C1, and we'll be going round in an anti-clockwise direction, and we'll be looking at the circulation around that. But what we're going to do is we're going to just not look at the circulation just around one, we're going to look at the circulation around the next adjacent one and the one after that, and we're going to add up the circulation around all of these, and we're going to make sure we use the right hand rule for all of them. So the circulation is going to be given by the tangential component of the vector field around your path. I've called that path C1. So if we sum up all of these paths from, let's say, L equals 1 to N, so L is the Lth path and N is the total number of the little area elements, so that would be down here would be a CL. So we're summing all of these circulations up for all of these little area elements. So the assertion we're going to have is that once we've summed up all of those little circulations, then what we're going to be left is just the circulation over the capping path. So we'll go back there, you'll see that. So if we were to look at this little path here, and then we were to add on the circulation around this little path here, well, the adjoining path is going to have equal but opposite circulation, so the adjoining path won't add any value to the overall circulation. And you can see that whenever we go into a little drawing here. So I've drawn two of the paths together, so there's one of the paths here, and there's the adjacent path here in pink, and you can see that the circulation here around this path 1, you can just call that path 1 and path 2, and then the circulation around that path is in pink, the circulation around that path is in yellow, and we can see that the yellow and the pink here are equal but they're opposite for the adjacent path. So it means that these cancel out, so you're only going to be left with, in the end, the circulation around the the outer perimeter. So that's going to disappear, and you're going to be left with just the circulation around the outer perimeter. Okay, so that's what this little equation here is telling us. So I've rewritten that again. So we're really saying that this factor of the circulation from A to B is equal to the negative of the circulation from B to A. So we can take this over to the other side. So when I add both together, we're going to get 0. So now what we're going to do, we're going to take this bit of information, we're going to continue as we did when we did the divergence theorem a few videos ago. So let's finish this off here. So we've seen this here from just the previous page there, from summing up the circulations over all of the paths is equal to the circulation round about the perimeter. Now what we're going to do is we can multiply by the small area element delta SL and divide by that delta SL, as you've seen that done previously as well whenever we did the divergence. And what we're going to do is we'll do that and we'll take the limit as the number of the faces tends towards infinity and the area of the face tends towards 0. And we'll bracket off this little section here because we've seen this before. This is nothing other than, from the previous video, the normal component of the curl. So it means that when we take this limit here, we're forming a surface integral. So we're forming the surface integral of the normal component of the curl of the vector field. Now, one other thing to note here that's maybe not obvious from the size of the drawing is that the perimeter here in yellow is actually the jagged perimeter that follows these linear polyhedra shapes. So as the number of these polyhedra tends towards infinity and the area of them tends towards 0, it just tends towards a continuous path represented by C. Okay, so down here we can then write that this value here, the integral round about the perimeter, will tend towards the integral around about a continuous path C. So it means that we can write this thing up here, okay, which just equals the perimeter round about the C, is now equal to, from what we worked out here, the normal component of the curl over the surface, the capping surface. So finally we can write out Stoke's theorem here, which tells us that the normal component of the curl of a vector field over a surface is equal to the line integral around about a path of the tangential component of that same vector field, where the C is the root over which the surface here has been capped. Okay, so you can kind of get an intuition for this if you were to, say, draw out some general surface here. And when we think about the curl, we're thinking about, the curl of the field, we're thinking about what happens whenever a small microscopic area here, and what happens, let's say for example it was the eddy currents in some surface of a water, so if we drop the leaf in, it would start twisting round. So we're looking at these microscopic twists, but we've seen that these microscopic twists, if we were to take one adjacent to another and we were to form the right hand rule for these, we could see that this would twist in this direction and this would twist here and that would twist here. But if we were to form the same right hand rule, then we would be saying that the second one here would twist in this same direction, but if this point here was touching that point there, then this twist and the pink twist and the blue twist would cancel. So all we would be left with would be the twist from the actual perimeter. And then if we were to take that up to all of the rest of the values here, all of the rest of these macroscopic areas up to a macroscopic level, then all we would be left with would be the circulation round about the line which is encloses all of this area which we've actually been looking at. Okay, so that's a kind of wordy or a kind of a heuristic or intuition behind the Stokes theorem. So what we're going to do now is we're going to look in the next video and see where we can use Stokes theorem. Okay, so thank you for listening, and I'll get you in the next video.